So today I'll be presenting the research summary and overview, which I conducted during my military service as a research officer at ADD. So my work mainly focused on AI and autonomy for defense technologies, especially on autonomous navigation in uncertain environments such as off-road conditions. The main theme of my research has been embracing uncertainties in off-road perception toward robust autonomous navigation. So during my service at ADD, I conducted research on defense industry, specifically field robots. So these are the main projects I participated on. So the main one is adaptive path planning based on situational awareness and dynamic model learning. So this is for high-speed navigation of off-road vehicles. So I participated in mapping and perception side mainly. So we construct the online map of surroundings without any prior knowledge of the environments. And we aim to make the vehicle navigation as fast as possible. And I also participate in projects on autonomous tunnel exploitation, so building a map of the subterranean environments and navigate and exploration. Also, I try to make the traversable area and object detection on adverse environment conditions more robust, which is more about domain adaptation and domain generalization. So all of these projects aims to make the off-road autonomy and off-road perception more generalizable and more reliable, which result in broadening the horizons of the off-road autonomies. And I have spent wonderful 3 years in ADD, and I actually was invited as a young researcher of defense industry and had a talk with Korean president last year. So let's start talking about the off-road navigation. So there are increasing demands for broadening the horizons of autonomous navigation into various environments. So in unstructured and uncertain environments, the vehicle navigation is quite different from the many other navigation technologies. So to make the navigation more safe and reliable in unstructured off-road environments, which have a variety of challenging terrain, and various autonomous techs should deal with uncertainties inherent in these conditions. So my research has focused on enhancing these systems to ensure robust performance in these complex scenarios and complex settings. So the main characteristics of off-road environments is that robots must operate and maneuver without any kind of predefined knowledge of the terrain. It also have limited sensor configurations, and it should be run on real time, and it should make the online understanding of this unstructured environment, which have more difficult and diverse representations. This necessity of online understanding and more complex understanding leads to inevitable and often massive amounts of uncertainties in the systems. So to make these systems more reliable, we need to deal with uncertainties. So actually, to operate more reliably in off-road conditions, higher levels of understanding of surroundings are required compared to other mundane stacks. So many people and many research use deep learning-based technologies. However, these deep learning-based features and method are unreliable and often make overconfident predictions in unseen conditions. So unlike structured on-road conditions, off-road autonomy often encounters unseen conditions and even more diverse representation of environments, which leads to a higher domain gap and consequently higher epistemic uncertainty when we use the data-centric predictions and methods. Therefore, traditional deep learning method can be frequently uncertain or even overconfident, potentially resulting in catastrophic navigational failures. Therefore, The central idea and question of my research for 3 years were how can we identify and eventually embrace and achieve much more robustness in the navigation. So my work focuses on developing methods to manage and utilize these inherent uncertainties, ensuring safe and reliable autonomous navigation in challenging off-road environments. So my research goal have been improving reliability and generalizability. So the main method and autonomy state I participated on was traversability estimation, semantic mapping, and object detection to deal with the dynamic environment and dynamic objects. And I also tried to construct the bird's eye view cost map given the limited sensor configurations. And also to increase the reliability and accuracy, sensor fusion is adopted. And to achieve the high-speed vehicle navigation, I also participated projects on vehicle dimension learning. And to achieve this and to improve these technologies, these methods are adopted. The main themes are self-supervised learning and meta learning, domain annotation, and evidential deep learning. And all of these are machine learning techniques that try to quantify or minimize uncertainties and make this the learning-based method more generalizable. And I also focus on computer vision techniques that can be adopted to autonomous text in off-road conditions, like semantic scene completion or object detection. So this is an outline for my presentation. So first of all, mainly I'm gonna present the self-supervised traversable estimation methods I researched on, and this resulted in several publications. The main algorithms are learning uncertainty-aware traversability from actual driving experiences of the vehicle. I devised a LiDAR-based method and an image-based method, and I also adopted meta-learning to minimize uncertainties. Next one is the unsupervised domain annotation. So I adopted the domain annotation techniques to make the object detector more robust in adverse weather conditions. And the next one is the evidential semantic mapping. I termed this evidential semantic mapping because I adopted the evidential deep learning to improve robustness of 3D semantic mapping in off-road conditions. So the main algorithm is the uncertainty-aware Bayesian kernel inference, which is the continuous mapping, and the Dempster-Shafer theory of evidence is adopted to accumulate the uncertain predictions over times, which result in more reliable result. And I also tried to research uncertainty-aware LiDAR image fusion. So the main application was BEV semantic terrain map estimation, which is kind of the cosmic construction. And in this research, we devised the uncertainty-aware fusion method to improve scalability for various sensor configurations and various environments because, in off-road conditions, it's really hard and time-consuming to construct the label data set. So using this fusion techniques and this method to improve scalability, we can make and learn the terrain cost map generation method in diverse environments. So I mainly participate in projects involving high-speed navigation with various uncertain settings. And I try to improve the system's generalizability and mainly focus on learning traversability. The first one is I try to improve the scalability of learning-based traversability method. So I noticed that the learning traversability method in the literature is limited to specific sensor configurations or vehicle types. Consequently, I devised a method that can learn traversability cost directly from robot terrain interaction data in a self-supervised manner without any kind of human labeling. So this results in more accurate representation of traversability, and as it does not require human labeling, we can learn vehicle-specific traversability in various settings. So, however, as the vehicle interactions are limited to actually traversed regions, which is only a small portion of the whole data, the predictions are subject to high epistemic uncertainty. So therefore, in this research, I proposed an anomaly detection-based method for identifying the regions with low uncertainties, which means it's safe to traversable. So, to learn the terrain's vehicle-specific traversability, recent research has focused on self-supervised learning method that leverage a vehicle's driving experience. So if we use the self-supervised approaches, as it used the actual driving experiences rather than human-provided annotations, it results in varied results and different predictions for different vehicles. So our method learns to regress the traversability that a vehicle would undergo while traversing such terrain. Moreover, our framework uses a positive online learning method that does not require any kind of human supervision to classify uncertain regions. So after learning the vehicle-specific traversability, we conducted the navigation experiments using an MPPI controller. So as the different vehicle has predict different traversability costs, it results in the different navigation result. So for example, an off-road vehicle can traverse through tough bumps, while a compact car took sharp steering to avoid them. Also, navigating without the identifying uncertainty, which we terms binary classification, or just regressing the continuous cost map, which is traversability regression, resulted in failure in our experiments. And we can also modify the various cost structures using the sampling-based MPPI controller. It can result in like different navigational result by employing different objectives. So we also demonstrated the efficacy of our framework using real-world driving data with our mobility platform in unstructured environment and also a public off-road driving data set. We also quantitatively evaluate the quality of our positive online learning algorithm. And our method showed a significant margin compared to other one-class classification methods for various data sets. After this research, I tried to incorporate visual data to more reliably identify traversable regions. And I thought that I could utilize visual data for identifying regions with high uncertainties. However, like varying visual appearances in off-road conditions led to high uncertainty utilizing a pre-trained model for visual classification. So numerous approaches utilize large-scale human annotated datasets, which can be unsustainable and even erroneous in some conditions, like off-road conditions. As off-road environments has varying visual appearances, traversability estimation in off-road conditions with the pre-trained the network can result in high uncertainties. And as like these public datasets or some datasets only contain observations for a specific and limited context, the traversable estimation in off-road environments with varying visual appearances frequently leads to unreliable results. So to learn the terrain traversability, I tried to similarly use the vehicle's self-supervision, which means we leverage a vehicle's driving experiences to make a self-label. And just using the just driving the vehicle and operating robot in various environments, we can easily obtain the self-supervised traversable label in diverse off-road environments. Manually annotating images for every environment is impractical compared to this approach. Instead, we can automatically generate labels for traversable regions by projecting the vehicle trajectories onto the image plane in a self-supervised manner. And this approach provides self-supervised traversable labels, which are particularly useful for learning how to navigate in diverse off-road environments. So in this work, we proposed the self-supervised traversable estimation method, focusing on visual data that can learn traversability only from self-supervisions without explicit labels. And these self-supervised labels are robust specific, meaning they can incorporate the navigational capabilities and characteristics of the individual robots. This method allows for effective learning of traversability without the need of extensive manual annotation in various environments in off-road. So to briefly explain the method, on capture data, the wheel contact points are considered traversable, and the occluded trajectories are filtered out. And also we use the like LiDAR points to conduct the occlusion filtering. And we also use the unsupervised LiDAR denoising to make the occlusion filtering in diverse conditions like off-road because it has a lot of noise particles in LiDAR points. We conduct the unsupervised LiDAR denoising. And trajectories are then projected to image coordinate, and these pixels are labeled as traversable, and remaining pixels are left unlabeled. So since no labels for non-traversable regions can be obtained, we know only the small portion of traversable regions. We aim to identify traversable regions more accurately only using these labels. And this algorithm is based on the one-class classification algorithm, which is also known as positive unlabeled learning. So for the one-class classification algorithm, the image is augmented and forwarded to a feature encoder. And as there exists like various representation of traversable regions in off-road conditions compared to the structured conditions. The representation of traversable pixels have high intra-class variation. So to deal with this issue, we adopt the 2D normalizing flow, which is the fast flow, to project complex distribution of traversable region features to a simpler distribution while avoiding a trivial solution. Then the feature embedding space is learned to maximize the cosine similarity between the features of traversable pixels and a positive center. And in addition to using positive data, we also utilize the unlabeled points to obtain more discriminative features and also prevent hypersphere collapse. The full features of unlabeled pixels are jointly self-labeled and clustered, with a set of learnable prototypes motivated by self-supervised clustering for learning visual representations. And the feature space is learned by fully utilizing both positive and unlabeled pixels by adopting the self-supervised clustering objectives, which result in enhancing the discriminative power of features for the one-class classification. So this algorithm is similar to the LiDAR counterpart of our algorithm, but we found that image features have more complexity, and this algorithm is not enough. So as the learned representations are still insufficient as we just try to learn the representation without the human supervision or label. So to supplement the representation power of features, the encoder is simultaneously learned with the contrastive pretext task of self-supervised visual representation learning. So using the features of augmented images, the contrastive loss pulls features of positive pairs while pushing away the features of negative pairs, resulting in more semantically meaningful and discriminative representations for traversability estimation. So after training the network with this only self-supervisions, the network can accurately estimate the traversability of image pixels in real time for the inference. So after the inference is much more simple. After forwarding the image to the encoder and the flow model, each pixel's traversability is determined by measuring the similarity with the positive center, which is determined in a random manner during the training. So we have conducted various experiments to analyze the effectiveness of our method. And here is the results of experiments using the publicly available dataset released 3D. So compared to the other method, which is just merely assessing terrain type based on texture. Our method have more identifies traversable regions more clearly and even more contextually significantly. And we also obtained our own data set in various environment and various settings like weather conditions or like road conditions and varying places, seasons, weather, lightning, terrain types, obstacles, and also lens conditions because we need to more thoroughly test the validity of our method for visual traversability estimation. So our method outperforms models trained with manual labels in a supervised way using the public data set. And this is due to the fact that our method exploits self-supervised labels acquired on the target distribution. So the model can estimate traversability much more reliably in the presence of distributional shifts compared to the supervised manner, which just used the public data set. So our method can be deployed in real time for high-speed off-road navigation. And the estimation results on visual data and LiDAR data are represented onto the bird eye view coordinate using the geometry of the LiDAR point clouds. And we generate the traversability cost map based on the Bayes algorithm. The traversability cost map generated from our method can accurately identify traversal regions that are safe to traverse in an online manner without like predefined or prior knowledge of the environments. So previous methods for estimating traversability often require retraining, and also struggle with generalization. So they tend to perform poorly when deployed in new environments due to their higher sensitivity to terrain variability, such as various conditions and distributional shifts. Therefore, models trained on a single environment exhibit high uncertainty and limited generalizability. So, like collecting more data from diverse environments and train a global single model, it can be a solution, but it results in higher aleatory uncertainties. For instance, LiDAR point clouds may capture similarly looking terrains, but the interaction between the vehicle and terrain can vary significantly. This variation makes it difficult for models to converge effectively when we train the model using the self-supervised traversable data collected from various environments. So to address these challenges and to predict and learn traversability more precisely, I identified the need for a global model that can learn from experience and adapt to new conditions and progressively reduces uncertainties during the deployment. And by leveraging meta-learning, I developed a model capable of accurately estimating traversability across various environments and also adapting to novel terrains through online learning. So first of all, we tried to generate an uncertainty-aware traversability cost map for safe navigation. So as off-road environments are fraught with bumps and obstacles of varying shapes, despite being in the same terrain class. So we estimate more nuanced and continuous valued traversable costs of the terrain, which can be defined using the frequency domain analysis of the IMU signals. And we project this continuous valued traversability cost on a bird eye view coordinate. And the traversability cost prediction network is trained to produce a dense top view cost map using a sparse single sieve LiDAR point cloud. So this network takes a single sieve LiDAR point cloud as an input and uses the point pillar based network to generate a dense cost map. And using this dense and continuous traversability cost map generation network, we perform online annotation with the self-label data as shown in this picture in an online manner, and it could be able to accurately predict traversability cost during deployment in a variety of environments, including the unknown ones. So the predicting traversability from LiDAR sensor entails a significant degree of uncertainties, as I mentioned before. So as there are a variety of terrain properties that influence traversability, like deformability, friction, and roughness, and this traversability differs according to a number of factors, while such subtle differences cannot be precisely captured. So to resolve this issue, the model is online adapted based on the recent experiences, by assuming that recent experiences have a higher probability of representing the terrain characteristics of the future trajectories. So we adopt the concept of meta-learning and model-agnostic meta-learning for online adaptation of the traversability model. And as a result, the model is capable of quickly adapting to a new environment based on its recent experiences. And finally, we integrate this component as a single system for navigation. So using the vehicle dynamics model, which is also learned with the active exploration, and we use the traversable cost map generated from our previous method, the navigation is performed using a sampling-based model predictive controller. And during the deployment, traversable data is self-labeled using the recent experiences and signals from the IMUs. And our traversable cost prediction network is online adapted to minimize the uncertainty and thus more accurately represent the environments. To assess whether our method can learn a global model that minimizes uncertainties in traversability estimation across various environments, we compared it to a baseline model trained without the meta-learning objective. So in various environment and category, our meta-learned model outperforms the baseline. The baseline model, which lacked the meta objective, struggled to converge during the training due to higher aleatory uncertainty in the ground truth traversability data, which is collected across diverse terrains. In contrast, our method, which adopts meta-learning objective, successfully handles this uncertainty by incorporating it during training and adapting the model during inference. And even without adaptation, during the evaluation process, our meta-learned method still outperforms the baseline, which means that the meta objectives helps find better initial parameters. Furthermore, the model's performance continues to improve as it adapts during the inference using recent interaction experiences. So for real-time performance, we just conduct like a few steps of adaptations during the model update. So to assess whether our method facilitates safe and effective navigation in a structured environment, we designed an additional offered environment with several unknown types of bumps. So the vehicle begins adaptation after encountering 3 types of unknown bumps, allowing it to generate trajectory that minimize disturbance upon re-encountering this kind of bumps. So initially, the predicted traversability for unknown bumps is not well differentiated due to the lack of prior information. However, as the network adapts online using recent experiences, and it already have the experiences of this kind of unknown bumps, the model that can adapt is now have knowledge of this kind of bumps. So it can differentiate these several kinds of bump effectively. And it begins to lower the predicted cost for bump and more effectively compare to various kind of bump and plan the trajectory, optimize the trajectory that can minimize the disturbance of the vehicle. So this adaptation allows the vehicle to successfully navigate by avoiding the more challenging bumps. And in contrast, the vehicle that does not conduct adaptation fails to recognize and avoid these difficulties, leading to a rollover. So this shows that online adaptation significantly improves the vehicle's ability to handle unknown terrains and navigate safely. So this were all about my research on traversable estimation. And so we need to construct the traversability cost map for more reliable and safe navigation in off-road environments. But I also noticed the need of reducing uncertainties in other computer vision-based technologies or perception stacks. So after encountering significant uncertainties in the open world navigation settings, so I actively sought method to minimize this uncertainty in perception. And actually, to address these challenges, I organized like seminars within my organization to discuss and explore solutions. So my main focus was identifying and minimizing uncertainties in machine learning based methodologies for perception applications. And just let me begin. So firstly, I focus on enhancing the robustness of object detection under real-world adverse weather conditions. So I proposed a novel domain adaptation method that can effectively address both the style domain gap and weather-induced corruptions. So our main idea was the domain gap between clear weather training data and the target data, which have like various weather corruptions, can be decomposed into two factors, which is star gap and the weather gap. So by conducting the unsupervised domain adaptation, which means we only have the ground truth uh, for the data set of the clear weather data, we can enhance the robustness and accuracy of object detection in rainy weather conditions and also the snow weather conditions, and also all other adverse weather conditions. So despite the success of beam learning-based object detection method in recent years, so making these detectors reliable in adverse weather conditions such as rain and snow remains challenging. To ensure dependability, it's crucial to develop a learning-based method that can effectively adapt object detector to these challenging conditions. So our approach focuses on addressing this need by creating adaptive technologies that enhances the robustness of object detection systems. And to adapt to various environment and various weather conditions, we should not use the like manual annotation. So our focus was improving the performance in adverse weather without acquiring labels on the target dataset, which is the probable setting of unsupervised domain annotation. So the previous approaches utilized the synthetic data, which used the model of weather corruptions, for example, snow or rain. So it generates synthetic weather effects on clear images and train robust models, or also train on additional rain removal or snow removal networks. And it has large limitations because it cannot capture the complex real-world weather effects, and it is shown that it has limited improvement in real-world performance. And also, if we just use the removal network, it has more time-consuming and it cannot run in real time. But, real-world label data is really hard to obtain, and so the synthetic data was used as an alternative, but it has a lot of limitations in real-world scenarios. So recent studies have focused on unsupervised domain annotation method to enhance the robustness of object detection. And this method adapts the model trained in the source domain of clear weather to the target domain of adverse weather by considering the adverse weather as a factor that contribute to the domain gap. So as this setting only have the ground truth of the source data, which is mostly the clear weather conditions, we can adapt the network to the target data set, which was captured on the adverse weather conditions, without requiring the ground truth labels of target domain images. And most unsupervised domain annotation method aligns the feature distribution of the two domains in a global manner using the adversarial training. And these existing UDA methods consider weather corruption as part of the image style and just globally align the source and target distribution. However, we noticed that like weather corruption is something different from the style gap or domain gap. So as some features are arbitrarily and severely distorted by weather corruptions, and it is like more corrupted in a local manner. So this method frequently lead to suboptimal alignment if we try to adapt the network for the target data set captured in adverse weather conditions. So consequently, they are only effective on synthetic datasets with minor domain gaps, and their performance decreases when applied to real-world datasets with a large style gap and complex weather corruptions. So we try to break down the domain gap into two distinct factors to maximize the efficacy of domain annotation on the adverse weather conditions. The first one is the style gap, and the next one is the weather gap. Style gaps are caused by variations in the operating environments, more related to global and semantic factors like background and color and texture, whereas weather gaps result from weather-induced corruptions like rain stains and snowflakes. Unlike style gaps, which are caused by global and semantic factors, weather corruptions produces arbitrary and localized image degradation that is hard to characterize using the prior knowledge of the model. So to bridge the style gap, our method aligns high-level style-related features similar to the previous approaches. However, we also use an attention model called CBAM module to attend more on the semantically related features. So as we decompose the image gap into two factors, we try to align the features that are more related to the style gap. So as the CBAM conduct the channel attention and also the attention on the image spaces, we align the more higher level style related features only. And to resolve the weather gap, the self-supervised contrastive learning is employed. Based on the assumption that each instance consists of an object and random weather corruption, our model encourages the similarity between instance features within the same class. So using the class classification result from the object detector, we have like multiple prototypes of each classes and try to pull the representation of the same classes using the unsupervised clustering objectives. And it results in a robust representation against corruptions because, semantically similar objects are induced to have similar representations. So we show that our method outperforms other method in real-world adverse weather conditions. And other domain annotation-based methods showed a significant improvement in performance only on synthetic datasets, but their performance on real-world dataset is only marginally improved or even decreased. And this implies that existing methods that globally align distributions are ineffective when adapting to real-world dataset with a large style gap, but also have severe weather corruptions. To further validate our model across a wider range of environments, we collect our dataset in adverse weather conditions using our platform. And we qualitatively showed that our method can more reliably detect the objects in various adverse weather conditions. And so we analyzed the efficacy of instance level weather align module. So this is the visualization of proposal assigned to each prototype in our rainy dataset. So each row displays the proposals whose instance embedding is highly similar to each car class prototype. So similar shaped objects with diverse corruptions and styles are assigned to identical prototypes, indicating that the effectiveness of prototype-based contrast learning. For example, the first row contains car proposals captured from a rear view perspective and showing varying degrees of corruptions. So each prototype represents the similar object representations regardless of the weather corruptions. So it means as these uh, object proposals has similar representations, we can reduce the weather corruptions more effectively. So additionally, I researched sensor fusion method for reliable off-road perception. My approach involved incorporating the neural network's perception uncertainty into semantic occupancy predictions, which improved the scalability of mapping in various off-road environments characterized by high variability. So creating the semantic scene completion-based bird's-eye view terrain maps from a sparse point cloud faces significant challenges in unstructured off-road environments. The accuracy is hindered due to uncertain and noisy textures and the inherent nature of the terrain representations. This process also heavily depends on sensor configuration, which can vary greatly even within the same project. So most dataset to conduct the semantic scene completion requires hand-labeled dataset with point cloud and semantics. However, in off-road environments, terrain classes change frequently and sensor configuration can differ widely. So as a result, a learned model tend to perform poorly when these changes occur. So this research aims to improve the accuracy of semantic scene completion in uncertain off-road environments and to improve the scalability of this semantic scene completion-based terrain cost map construction to diverse environments and sensor configurations. So while label 3D datasets can create bird's-eye view ground truths in constrained and limited environments, their occasional cost in diverse environment and the limited applicability to specific sensor configuration and class definitions pose challenges in off-road conditions. So to ensure reliability and scalability in various settings, we adopt a pseudo-labeling approach for generating the ground truth. So this strategy alleviates constraints associated with the scarcity and expense of the acquiring 3D labels, enabling training across a wide range of off-road scenarios. So a pre-trained 2D image segmentation network derives semantic segmentation result from past and future images, and we accumulate these predictions into the bird's-eye view coordinate. So these outcomes are aggregated using the paired point clouds and then projected onto the bird's-eye view grids to generate the pseudo label. And each grid determines a pseudo label through the argmax operation. And also, its uncertainty is also quantified to conduct the uncertainty-aware optimization. So as we obtain only the pseudo label, we maintain the uncertainty information, which means that if the semantic prediction result is not consistent in the multiple time steps, it means that this label is not reliable and it should be weighted less during the optimization process. So our network takes the input from single chip LiDAR point cloud and an RGB image captured by the front camera, producing a dense semantic terrain classification map in bird's eye view as a result. So the extracted features from the image and point cloud are obtained through the distinct encoders, which is based on the voxel features. And these image and LiDAR features are fused using the multi-scale attentive feature fusion method. So we conduct the attention during the fusion sensor fusion and try to complement each modality's feature using the attention module. And it is integrated into each level of the 3D unit for each modality. And these fused features are passed to the 2D unit-based network to generate the dense semantic terrain classification map of local surroundings in bird's eye view. And during the optimization process, we use the uncertainties of the pseudo labels. So each pixel's optimization is weighed with the uncertainties to make the optimization and learning with the pseudo label more reliable. So this is the result of our method. So our method successfully predict a semantic terrain map with the LiDAR image fusion. So for instance, our method accurately identifies puddles and dirt in bird eye view maps while preserving the geometrical structure of the scene. So however, the camera-only method excels in extracting semantic information, but it fails to represent a map with accurate geometric structure in the complex off-road scenarios. So camera data can deal with have more higher semantic information, but it lacks the geometry information, which is essential for constructing the accurate semantic accurate map in the bird eye view space. On the other hand, LiDAR-only method can accurately construct a map, but it lacks the semantic details, so it is vulnerable to the semantic classification of terrain. So using the uncertainty-aware pseudo-labeling, we can deal with the domain shifts more reliably. So if we use the image segmentation network that is trained on the summer dataset, and there is a huge domain gap between the summer dataset and winter dataset, and we just use the image segmentation network pre-trained on the summer dataset and use this network to construct the pseudo label for the winter dataset. And if we optimize the network using the uncertainty-aware optimization, it can still construct clear and reliable semantic map as shown in the below. And moreover, I adopted the uncertainty quantification method to deal with neural network perception uncertainties in off-road environment. So the goal of this research is to construct reliable semantic map in off-road using the uncertainty-aware semantic segmentation based on the evidential deep learning. So existing semantic mapping method face challenges in constructing reliable map in off-road conditions due to the perception uncertainties. So we propose an evidential semantic mapping, which can enhance reliability in perceptually challenging conditions. So we estimate the uncertainties of network's prediction by modeling a second-order Dirichlet distribution based on the Dempster-Shafer theory of evidence. So the network is trained to compute parameters for the Dirichlet distribution from which the uncertainty of prediction is calculated. So compared to the conventional method, which can be overconfident, or we cannot deal with the predictions we cannot differentiate the predictions that is certain from the uncertain one. And if we use the Dirichlet distribution, we can also have the predictions in the same manner, but we can quantify the uncertainties of these predictions. So this semantic uncertainty is incorporated into the uncertainty-aware Bayesian kernel inference, which can focus on more certain predictions when constructing the semantic map. So it can prioritize more confident semantic predictions when accumulating semantic information for the mapping. So as shown in this picture, in this figure, so the original semantic mapping with BKI framework result in unclear and messy result due to the semantic uncertainties if we use the semantic segmentation network. And this is mainly because the scene is really like has high variability, and the road the image is not clear, and it has like higher uncertainties in the semantic predictions. And even with these noisy predictions, we can clearly and reliably construct the semantic map using the evidential semantic mapping framework. So the task is uh, constructing semantic map given 2D RGB images and 3D point cloud and pose informations. And in this setting, the 2D semantic predictions are projected on the corresponding 3D point clouds to obtain semantic points. And the semantic points are used as the input for the mapping framework and we use the semantic points of various time steps to construct the final semantic map. So the mapping framework mainly updates the semantic information in the map representation recursively. So, but in the offered environments, there are large illumination changes and more unstructured details of environments with respect to the urban settings or structured settings. And it leads to higher intra-class variation and varying visual appearances, leading to higher aleatory uncertainties. And this also induces significant training set and test set inconsistency, which contribute to the high epistemic uncertainties. So it has high aleatory uncertainties and also epistemic uncertainties. And to deal with these uncertainties, so to construct a more reliable semantic map in offered conditions, we need to deal with both types of these uncertainties. So we hypothesized that we can improve the robustness and accuracy of semantic mapping by considering focusing more on the uncertainties of the network, which is the predictive uncertainties. So we adapt evidential deep learning into the semantic stagnation network, which can estimate uncertainties with respect to each semantic predictions of 2D pixels. Specifically, the evidential deep learning estimate predictive uncertainty by modeling the second-order Dirichlet distribution over the semantic probability distributions through single forward pass. So just like adapting the network on the last layer, we can obtain the semantic predictions and also semantic uncertainties. And this semantic prediction is not like discrete type. It is continuous if we just use the scores of the predictions. So this can deal with aleatory uncertainties, and the semantic uncertainty is all about the epistemic uncertainties. And both the aleatory uncertainties and epistemic uncertainty information is preserved. So this is the overview pipeline of our uncertainty-aware semantic BKI framework. So with an evidential stagnation network trained by evidential deep learning, input data image is processed to derive continuous semantic probability and also its predictive uncertainties. And these 3D semantic points are then integrated into the semantic map through Bayesian updates using the uncertainty-aware BKI update. And it results in a dependable semantic map and also a variance map which can be used for the navigation purpose. So we also try to replace the Bayesian kernel inference, which is using the like predictions of local neighbor to construct the continuous semantic map using the Dempster's combination rule to more accurately accumulate multiple semantic information over time. So Dempster's combination rule is quite different from Bayesian method, and it can deal with the uncertainties. It can fuse the uncertainty information of multiple time steps more accurately. And as a result, we can get the uncertainty map and construct the uncertainty map in Foxa spaces more reliably. So our method extend the belief mass to be distributed around its exact position, 3D position, instead of regarding it as only exists only in the observed position. And we adopt the similar adaptive kernel inference, and we also filter out some semantic points that has higher uh, higher semantic uncertainty than our predefined threshold. So the main concept is we filter out semantic points that have higher uncertainties, and we prioritize the predictions with lower uncertainties during the fusion process. So this is the result of our work. So compared to the previous method that does not uh, utilize the semantic uncertainties during the mapping, our method more clearly construct the semantic map. And we can also construct the uncertainty map, which is a variance, more clearly compared to the other method. And we also noticed that if we use the Dempster's combination rule during the mapping, we can more accurately construct the uncertainty map as it represent and fuse the uncertainty information more accurately. So the overestimation error is resolved in the uncertainty map in a more qualitatively manner. So as you can see here, the incorporation of semantic uncertainty helped to construct more accurate and clear boundaries between the other semantic categories. So we also analyzed the method quantitatively, which resulted in better performance compared to the other methods. And after conducting all of this perception research through my service, I concluded that these all uncertainty-aware perception method should be integrated into decision making and control for successful navigation under uncertainties. So I also participated in vehicle dynamics learning that can quantify uncertainty using a probabilistic ensemble neural network. So this is the overview diagram of the model-based reinforcement learning framework with dynamics learning. So in the exploration phase, the parallelized ensemble neural network is assumed as a robot dynamics, and it outputs the estimated posterior distribution of the next state. So our goal is to conduct active exploration, and we quantify the epistemic uncertainty by measuring the ensemble disagreement. And in the deploy and using this quantified uncertainty, we conduct the active exploration to learn more robust dynamics model. And during the deployment phase, the neural network dynamics trained during the active exploration is applied directly. And we can also perform uncertainty-aware control using the quantified uncertainties. So the probabilistic ensemble neural network is used to model the epistemic uncertainty of the model, to calculate the epistemic uncertainty of the model. And the model to perform, like, the model is performed with the active exploration, resulting in the efficient collection of training data and effective avoidance of uncertain state action spaces during deployment. So in the deployment phase, the neural network dynamics trained during the active exploration phase is applied directly to perform uncertainty-aware control. So we integrate the traversable map with this learned dynamics model in a zero-shot transfer manner using an MPPI controller.